the I/O section, or input-output section. Anytime you hear the words I/O, it means input-output. And basically this is the section of the PLC that connects to all the field devices, and what that means is that all the switches, which are inputs, and all the devices that are outputs are connected to this portion of the PLC. Some PLCs are set up where they only have so many inputs and outputs, and these are terminal points that you can connect wires to, and some are modular where you can add or remove or change out various input-output types of modules. A rack-based I/O section has multiple I/O modules that interface to a backplane or a rack of some kind. So you've got the concept of slots and the various input-output modules. The nice thing about this is that you can configure it however you want. You can choose, if you need more inputs than outputs, no problem, you can do that. So the input modules accept signals from the system, from the real world, from the user who's controlling it, whereas the output section is interfaced to the machine to make things happen on the machine. What's shown here is an 8-slot chassis. The chassis is the thing that houses the I/O modules, that accepts them, that it can be plugged into. And the logical rack is really just an addressable unit of 128 input points and 128 output points. Now, a lot of times it's not handy to have all of the wires from all the sensors and all the outputs run back to the PLC. That's called home running the wires. It means that you run the wires from every switch and every output device all the way back to home, to the PLC. Sometimes you want to have what's called remote I/O, and what that means is you just, instead of having every single wire necessary for every single switch, for example, what you have instead is a remote I/O module that has the wiring connected for all those switches, and then there's communication to send the status of all those switches back to the main PLC that's actually doing all the processing of the inputs to decide what the output should be. And of course, that remote I/O not only has input, it also potentially has output in order to drive actuators and things that are remotely located. And the whole point here is to not run so many wires. If you do run wires all the way back to the PLC, as I said, that's called home running the wires, and that's the opposite of remote I/O. Now, it's also possible that the PLC itself would have some I/O on it as well, and a lot of times you can have multiple remote I/O devices. But the point is that it reduces the number of wires going all the way back to the PLC, which can be quite a distance in some cases. In many, it's not uncommon for a real process in the real world to be quite large, where running, hundreds of sensor wires all the way back to the PLC just doesn't make sense. And this is even a little more, how can I say it, distributed I/O is really the idea that this communication is more like a network. And so in the sort of the old days, if you will, these were proprietary, typically, maybe even RS-232 communications, and you had to have a remote I/O device that matched the PLC, and to some extent that's still true today. But the communication line nowadays are much more commonly Ethernet or something like that, where technically you don't really even need a PLC close by. In fact, a lot of times you don't even need a PLC. You can use a computer instead with a bunch of distributed I/O modules. So the status of all the inputs and outputs has to be stored in the PLC's memory, and the way you keep track of it, the way you figure out which particular little bit of memory corresponds to which input or which output switch or device, is by addressing. And addressing is just, it's a number or it's a label that indicates where that particular input or output is in the PLC's memory. Now, sometimes they'll use what's called rack and slot based, and this is common on Allen Bradley PLCs, where you have a rack number followed by a slot number essentially, and then typically a bit number as well. But tag-based addressing is used with other Allen Bradley and ControlLogix controllers, where basically the input or output is named, but that name is associated with a very particular address. So here's the format for PLC 5, which is a fairly old PLC, but many PLCs operate on some variant of this. And so the first thing at the beginning is really just the file. It's like this is an output address example. where you begin by O. O is the output file. In other words, that's the page of memory that stores all the output bits and what they should be. And there can be more than one file of outputs, just depending on how many output modules you've got in the PLC. So you'd have, the 0 would be, file number 0. Now, a lot of times this is redundant, so that O and 0 are redundant, and you don't have to type both in for the PLC programming software to know what you're talking about. But after the colon is a file delimiter, and what comes after that then is the rack number, and then the group number after that, and then finally the slash is the bit delimiter. That means what follows is the particular bit, in other words, the particular terminal point, the particular input or output point, in this case output point, that you want to address. So you can see examples of some PLC 5 addressing here. SLC 500s are still extremely common in industry. They're called SLC 500s. That's not really their name, they're SLCs, but people call them SLC 500s in industry. And they're kind of like their addressing is very similar to what you saw before with the PLC 5s. There's a little bit of variation where you've got the colon and then a slot number and then a period for the sub-element number. So it depends on what this is. If it's a real-world address, then the first thing is the module type, and then after the colon is a slot number, and then after the slash are the terminal numbers. But if it's a memory address you're talking about, then you're talking about a particular file or file number, the element within that file, sub-element after the dot, and then the slash gives you the bit number. So it's the same thing in a sense. It just tells you what real-world address corresponds to what memory address. So every single input and every single output on a PLC has to have its own unique bit, its own binary digit that can be a 1 or a 0. Of course, the inputs drive that bit and turn it on or off. The output bits drive the outputs themselves in order to make things actually happen. So what happens is, switches come into the PLC and set or clear bits. Those bits then go into the program and drive the logic, and then the calculations of the outputs, the O:3/0 in this case, then is written into a particular memory address, which then drives the output to either be on or off, in this case off. Now, binary or bit inputs and outputs are not the only type that are available. There are also analog input and output modules, and they use words of data. Instead of bits, which are a single on-off thing, they use a whole word, which would be 16 bits typically. And usually you don't have to reference the individual bits of the address, but you can in many languages. Now, in some you can't. In the click PLCs, I have not figured out how to. I could take a whole word of memory and figure out whether a particular bit is on or off by using bitwise ANDing and ORing, but I haven't found a way to address a particular bit of a particular word, whereas you can do those things in Alan Bradley's programming language. So things like thermocouples require a whole word of data, because think about it, a thermocouple is sensing temperature. Well, technically it's sensing millivolts, but it's converted to temperature, but it's a continuous thing. It's not an on-off thing. And you might say, well, all I care about is if the temperature goes above a certain level. Well, that's fine, but that has to be in your program. Your thermocouple is going to give you whatever the current temperature is, essentially, once it's been worked up from the voltage signal to an interpreted temperature. And what you do with that number in your program is up to you. You can do a comparison and decide that, once the temperature reaches a certain level, I will or will not do things. For example, in my home heating system, I don't allow my heat pump to turn on unless the temperature is above 40 degrees outside. And I don't allow, I allow it to remain on and functional until the temperature drops down to 35 degrees outside. And the temperature has to go back up to 40. So I've got a hysteresis band, if you will, or a dead band there. It would really be a hysteresis band because it's not dead, it can operate. It just operates differently depending on whether the temperature is rising or falling, so that would be hysteresis. Now you can have analog outputs as well, and an analog output could be, as shown here, some type of meter that shows the level of something. And unfortunately, it kind of looks like a clock, but Typically, maybe a temperature display, or it could be, some type of actuator, a control valve, for example, where the valve's not on or off. It could be turned on and off continuously between a range of values. Now, of course, these require an entire word of data in order to use analog I/O. Now, ControlLogix controllers use tag-based addressing. So you see how the address is laid out here. This is not something I'm particularly familiar with. If I used it, I would know more about it. But it's just a tag-based address, and it's nice because you can give it a description. Of course, you can give descriptions to everything. It's really important when you program PLCs to put comments on your instructions. In other words, all of the memory addresses need to be labeled, at least the ones that you're using, so that someone else can read the program and understand what it's trying to do. So we've got our description that's assigned to an alias tag. The alias tag then points to the base address, and you can see the base address there, and then the input instruction. So it's important to understand that no matter what flavor of PLC programming language you're talking about, these instructions are just instructions that go and reference particular memory locations that are associated with particular inputs and outputs, if it's an input type address or an output type of address. Now, of course, in PLCs there's other memory as well. Alan Bradley, for example, has files that are supposed to be all integers, or that are supposed to be all bits, or that are, I'm trying to remember what else they've got. They've got a timer file, a counter file, and it's a powerful language set because you can access these things at the bit level or the word level and do some interesting things with them. Whereas in the click PLCs, it's a little more tied down. Fortunately, most of the time, you don't have to access, a bit of a word. If it's supposed to be a word because it's a number that you read in, why would you want to read a particular bit of it? Most of the time, you don't really need to do that. It's just more advanced PLC programming that needs that. So click PLCs can do 99% really of what most PLCs do. And the nice thing, of course, is that they're less expensive. Now, when I was talking before about distributed I/O, I mentioned that you can also use a PC as a PLC. It's not really common, but it can be done. And there are PC-based controls, and they're run on hardened computers. The problem is, okay, the impetus for using a regular off-the-shelf PC is that it's inexpensive. The problem with that is that it's not hardened. It needs to be in an air-conditioned room, right? Can't get too hot, can't get too cold. It's sensitive to dust, and if you don't take care of it, it won't function properly. I used to work as a computer technician for a little while, and I remember several PCs and computers that people would bring in, and they wouldn't work for whatever reason. And it could be a bad graphics card or bad memory was very common. I'll never forget, there was one particular computer for the year and a half I was working in that industry. They brought it in and it just wouldn't turn on and work properly. As soon as I opened up the case, I was just amazed. I had never seen dust quite this thick. The dust was literally a ½ inch thick inside of this computer. I don't know how long it had been that it didn't work. I don't know how it had set and accumulated that much dust. But the first thing I had to do to even do anything was to clean it out. So I took it to the back dock, got some compressed air from just an air compressor, just got a blower gun, and blew the thing out. I mean, just got rid of all the dust. And actually brought it back to my bench, plugged it in, and it just worked. All it needed was to have the dust removed from it. I don't know electrically how it was causing problems, but obviously it was. And it was just amazing to me to see that much dust in the first place, and that took care of the problem completely. But it did. The PC turned on, worked just fine, and I called the customer and said, hey, you just need to clean your computer every now and then. But there's a lot of variety in this area, and you really need an industrial hardened computer, something that can take a little bit of abuse in terms of temperature and dust and so forth, because the goal of a PLC is for it to be easy to debug and change, but also for it to be able to work in an industrial environment. And one of the other problems with PC-based controls is if the I/O needs to be connected directly to the PC. Now, if you're using distributed I/O and you can connect a bunch of remote I/O modules, to the PC, then it's not so bad, because the PC can be set into an air-conditioned office or something and operate the process over a network, for example, and then it's not so bad. But there again, PLCs are made to be extremely reliable, not only against dust and dirt and obviously you don't want to pour water into them or something, but also against electrical noise and so on. One of the other issues with PCs is trying to connect all the I/O. If you don't have distributed I/O, PCs are set up in a standard way where you can see the slot here, the card that plugs into the computer. That height of that tab and the width and everything, that's a standard that's been around for quite a while now. And connecting enough I/O to it is really not practical. So that's one of the other limitations of using PC-based controls. Now, some modules are not just input or output modules. They are combo or combination modules that have some inputs and some outputs. And so the nice thing about this is you can take up one I/O slot, or have one card, or have something that's a little less expensive typically in terms of space or cost, that has inputs and outputs on it. And so there's an output section and an input section that are separate from each other, but it provides both functionalities in one card. Now, the I/O module itself is typically made up, well, always made up, of a circuit board, and has some terminal assembly where you can connect wires to it so that you can connect either the output devices or the input devices in order to wire up whatever needs to be wired up on the machine. And then here's a really important feature of every PLC I've ever seen, and that is plug-in wiring terminals. If you think about it, if you've got a module with even 8 different inputs, what if that module goes bad? What do you want to do? Well, you want to replace it. Well, do you really want to unwire 8 wires plus probably 2 or 3 that are required as well? So you've got 11 wires or 12, and you're trying to figure out where they go once you get the new card in. Well, the whole idea behind a PLC is to have something rugged and reliable, and when it's not, have it very serviceable. And so what you really want to do is be able to just disconnect all those wires at once, pull out the module, put the next one in, and plug it in and turn it back on and go in a couple of minutes at most. And that's what this plug-in wiring terminal strip allows you to do. Now, each manufacturer does a little bit differently, but the idea is that you don't have to actually unscrew the wires from the terminals. You just pull the whole strip off, new module, plug the strip back in, and away you go. Because the module itself is not all that critical. I mean, the module, yeah, you need it, but it doesn't have any programming in it, right? And so you want to maintain the wiring connection. If you have an equivalent module and you plug it in, then all of your input or output points are at the exact same address, and your program can just be turned back on and run. Now, cards vary in the amount of inputs or outputs that they carry. I've seen up to 64-point cards. Of course, they're very tightly connected together. They don't actually have screw terminals on the face, because 64 screws would be hard to fit on these relatively small module faces. And this is a high density. Now you can have even more. I think that some even have 128 inputs or outputs. But it's a space-saving thing, and often you don't need high current capacity. See, what's really going on inside of the module is that current's being switched on or off, especially if it's an output. And so the tighter you pack it in, the higher concentration of switching elements, and therefore either you run out of space because they're relays and they're relatively large, or you run out of current capacity where you've got to fit 64 transistors or so into the circuit board in order to have one for each one of the output devices or even input devices. And you just run out of space. But there are high density, and typically they just can't handle as much load as the lower density ones.